They've changed. Oh, yep. So right. Growth spurting baby galaxies.
Yes.
Go to it.
So I changed my title slightly to growth spurting galaxies, baby galaxies. And I mean, after hearing all these nice introductions this morning, I hope I don't need to convince you why the high redshift universe is actually very interesting for us. I just brought up this slide because just to bring back the point again, I mean, there's really a lot happening during the first billion years. I mean, you have cosmic reionization of the IGM. You form the first galaxies, and not only the first galaxies, but also the first black holes form during that time. And what I would like to do during my talk is, after you heard a lot about observations, I'm going to show you some results from numerical simulations that we run, trying to understand how these baby galaxies form and what actually their impact is on the surrounding IGM in terms of reionization and on their hosting dark matter halo, depending on how far I get in my time. So let me just bring that up. You heard a lot about the specific star formation rates. So if you look at high redshift, it seems to be an increasing function, and maybe the function seems to continue increasing or becomes flat at high redshift. But nevertheless, you seem to be forming more efficiently per unit mass stars at early times. And if you plot that, these results as a function of specific star formation as a function of mass, it becomes even more dramatic. If you look at the redshift 6 data points from Stargardal, you find galaxies around 10 to the 8, 10 to the 9 solar masses have rather high specific star formation rates. In fact, these specific star formation rates are as high as you only find them at later times in scuba sources, submillimeter galaxies. Now, we already heard a little bit about merging. Of course, there's also stellar assembly happening, not only star formation in situ. And what you can do is you can just go ahead and calculate the dynamical friction time scale under the assumption that you have an equal mass merger and overplot them over the specific star formation rate. And this answers something that we were discussing earlier. At high redshifts, the universe is so dense that dynamical friction timescales are actually quite short, and you build up galaxies through mergers quite efficiently with respect to in situ star formation. Or in other words, during one dynamical friction timescale, a galaxy can grow much more by the mass that falls in than by in situ star formation, if a merger happens. But of course, not every galaxy is going through a major merger. Now, to answer this and other questions, we embedded in a numerical simulation project in my group, in which we tried to simulate the first billion years with high resolution. So what we did is we used the Gadget 2 code and used the code that was used in the OLS project. This is a well-tested code which included star formation, metal enrichment, metal line cooling from 11 elements, black hole growth, the seeding of black holes, and supernova feedback. So what we did is we added on top of that molecular networks, the cooling from molecules. We added pop-3 star formation and the seeding from these dying pop-3 stars of black holes. We further added dust from pan-stability supernova, from AGB stars and type 2 supernova. We allowed that dust to be actually destroyed to see how much dust is there by thermal sputtering. We also included in one of our simulations a Lyman-Werner background to see what the effect is on destroying actually molecules in the gas, trying to see actually how you change the collapse of gas. And in post-processing, we coupled our simulation to the radiative transfer code simplex, trying to see what we can learn about reionization, cosmic reionization. So this project, we called it the first billion year simulation, or Phoebe, is a suite of different simulations of different box sizes. And the highest resolution, largest box in our set is 8 cubic megaparsec with 2 times 1368 cube SPH particles. That gives us roughly an SPH mass of 1,000 solar masses per SPH particle. So this is actually quite large, and what we did in our approaches, we did not what people sometimes do, which is going and zoom on an individual object. We really wanted to resolve the whole box with the same high resolution to try to understand what's the effect on the environment. So you mean in terms of gravitational softening, or in terms? I have that number. I'm jet lagged. I have that number.
It looks like it might be like a KPC.
Well, actually, yes, we are at KPC level, clearly.
So
sure.
Do you think that's adequate?
For the first billion galaxies?
Yeah.
Why not? No, sorry. No, sorry. Well, okay, I need to rewind for a second. So look, we are actually, our gravitational smoothing is clearly under KPC level, right? So I can show you actually later on also density profiles of dark matter halos. We are clearly below KPC levels. We are resolving tens of parsec with our simulation. So
Well, not through gravitational softening.
no. The gravitational softening is not KBC. That's what I'm trying to say. That was the mistake.
Okay, so the question is, what is it?
No, we are at a parsec level.
Parsec level.
Yes. So I can show you. It comes later on. It comes later on the density profiles, right? So let me just show you the mass function that we get from our simulation. So one of the things we try to see is if our mass function actually has converged, and we try to do that by using actually simulations of different resolution. So there's always a factor 8 difference between these in terms of mass resolution. And here the results from Gonzalez et al. For the mass function. What you see is that we actually match, well, let's say we match the data, observed data here, and that's our prediction basically for the faint end slope. And the faint end slope is alpha of minus 1.65, which is less steep than what we have maybe heard this morning, but it's still okay in terms of the observed data. So it's still consistent with, in some respect, with the observed data. The other thing we try to see is what our simulation predicts in terms of star formation rate. This is now, again, we heard of the Smith et al. Data. What is the number density of galaxies of a given star formation rate? And you see, again, we match quite well the low end of those star formers. Of course, here, this end, we're not simulating since our box is too small. So it seems like we're in quite good agreement there. And again, we also find the relation between star formation rate and stellar mass. And here, this is the data from McClure et al. We basically match, again, this region of observations, but that doesn't need to mean much because as you look at it, it's really quite a large scatter there. Now, one could argue everything is fine and good, but there's, of course, things that don't match. And what I'm showing you here is the specific star formation rate as a function of mass again, and that's the Stark et al. Data. Around 10 to the 8 solar masses, we seem to not get up to such high star formation rates as observed. Now, is that a problem of the simulations? It could be. Maybe there's some physics missing. However, I mean, I think it'd be very interesting, and we heard about that this morning, to get more data in that mass range, trying to see if this is maybe just a selection effect. These are outliers, and there's actually the bulk of galaxies really lying here. And that's what the future observations might need to tell us.
You also need a selection effect in your simulation.
Well, yeah, I have a small box, so sure, it could be. Yeah, absolutely. So that could also happen, indeed. Yeah. So, right. If the stellar masses come down, you go up, right? So it goes in the other way. So, okay. Well, I mean, we heard a little bit about star formation and stellar mass buildup being smooth as a function of redshift. And we looked into that actually in our simulation. And what you see here is a function of mass, typical galaxies, so 10 to the 6, 10 to the 7, 10 to the 8, 10 to the 9 solar masses in our simulation. Here again, function of time, the star formation rate. What you see, indeed, the buildup seems to be smooth. You have a smoothly increasing mass buildup, a star formation rate, if you like. However, if you go to lower galaxies, it becomes all very much more spiky. It's not that smooth anymore. And the reason for that is twofold in our simulations. One part is that actually supernova feedback is quite efficient in stopping star formation instantaneously and basically shutting it down. However, you have a growth of gas. There's newly, freshly supplied material that constantly comes in and rejuvenates star formation, which gives you all these spiky features in those low-mass galaxies. Now, why is that not the case here in the massive galaxies? Because supernova feedback in those is not as efficient. And to highlight that point more quantitatively, here you see basically what our so-called mass loading factor is in the simulations. Mass loading defined as the mass, the outflow mass that goes out of the virial radius, which has escape velocities larger than the escape velocity of the halo, divided by the star formation rate in the halo. That's how we define it as a function of stellar mass and star formation rate. So you see, indeed, the low-mass galaxies show higher mass loading than the low-mass galaxies, so you're much more efficient in blowing out the material in those objects. And that's the reason for that spiky feature I showed you earlier. Now, to just visualize that a little bit more, and I hope you can see it, even though it's quite bright here. So here on the left, density and temperature. On the right, the metallicity of the material. So you see, you form the galaxies, and that's, again, just the first billion years. You start forming your first galaxies. The first enrichment processes happen. You have your first supernova going off. By the way, what you just saw was reionization. Everything got a little bit hotter here. Now you see outflows from that galaxy due to supernova feedback. You see these beautiful fountains going out. And if you look very carefully, you can see also there are hot regions there just at the borders of those fountains going out. You see them as red here, so red being hotter color. And you see these fountains of metals actually go quite out of the galaxy and are able to enrich surrounding neighborhoods quite efficiently. Now, what are these baby galaxies doing? So one question we wanted to answer is what's their contribution actually to reionization? We heard this morning that low-mass galaxies might actually be a very important source of photons for reionization. And what you see here is basically 3 panels that summarize our results that were achieved by running simplex in post-processing, including hydrogen and helium ionization. Now let's first focus on the middle panel, which shows you the Thomson optical depth, and this is the WMAP data. What we show here is basically the contribution from halos of different mass. If we just focus, let's say, here on the solid line, that's the contribution from all halos in our simulation. And you see that we're basically matching the Thomson optical depth. That means we managed to get reionization early enough in our simulation to be consistent with the results from WMAP. Now, if you look at the fraction of ionized, the ionized volume fraction in our simulation box, and here again split up by different halo masses. So this line, the green dashed line, is basically all halos below 10 to the 8 solar masses. The blue dashed line is all halos below 10 to the 7 solar masses. You see, most of the volume is ionized by halos below, between 10 to the 7, 10 to the 8 and 10 to the 7 solar masses. Okay. This is the redshift. That's the redshift. So we're starting redshift 20 down to redshift 6. Oh, yeah, sure. Right, and that will become a little bit more clear here on top. That's the next plot. So you can ask yourself, where's 50% of all the photons that we see coming in? And these are all coming from halos below that solid line at any given redshift. So this is basically answering your question. So as you go down in redshift, and as you see, ionization in our simulation is basically complete around 10.5, which nicely coincides with the WMAP data. You see at that redshift, it comes mostly from halos below 10 to the 8 solar masses, half of all the ionizing photons. Now, that's interesting because it basically means these small galaxies indeed are able to possibly reionize the universe. And only at later times, the massive ones need to kick in and help keeping the universe ionized. Now, we looked into that a bit more in detail here as a function of stellar mass. Here on the bottom plot, you see basically the number of ionizing photons that make it out of the galaxy divided by the number of atoms that they need to ionize. And if you want to achieve ionization, you need to be here at that line. And what you see is basically this ratio as a function of redshift for different galaxies of different mass. So there's a lot of proto-galaxies, even baby galaxies with less than 10 to the 4 solar masses that contribute a lot of ionizing photons at high redshift. But then coming to this critical time when you actually achieve ionization, you have it being achieved by galaxies less than 10 to the 6 solar masses. They, at least in our simulation box, provide a large fraction of ionizing photons. But again, I mean, what is true here is this is an 8 megapart, this is a small box. So we're missing actually large high sigma fluctuations. So large galaxies that can contribute to ionization are not in that simulation. So they could actually contribute even more photons. Nevertheless, it's very interesting to see that these small galaxies provide enough photons to do ionization. Only at later times, these massive galaxies actually contribute most of the ionizing photons or most photons in the universe to keep the universe ionized. So why is that? Why do we actually find that in our simulation? And that's what I'm trying to show you here as a function of redshift, the escape fraction from galaxies living in halos of different mass. Okay? So the least massive halos, in our case, these 10 to the 7 solar mass halos, dashed line, and then 10 to the 8 solar mass halos, dotted line, and 10 to the 9 solar mass halos, dashed dotted line. I'm sorry, I'm totally jet-lagged still. So there are two things I would like you to take away from this plot. This is at least what we find in our simulation. One, escape fractions are a strong function of redshift. So there's not one escape fraction that you should be using. Second, escape fractions are also a strong function of mass. The escape fraction in massive galaxies, okay, as indicated here, is much lower than in less massive galaxies at any given redshift. So why is that? Both is actually, again, an effect of feedback in our simulation. So what happens is, I showed you, these small galaxies are very heavily affected by feedback, which causes to blow out the gas to make channels for the photons to escape. Okay? That's why low-mass galaxies have high escape fractions. Massive galaxies, at least in our simulation, don't have that efficient feedback, and therefore the gas is there, the column densities are higher, and your escape fractions are lower. As time goes on, and feedback has been working on the ISM, you're actually generating more and more channels, and you're able to actually have more photons escape into the IGM. And that's why you get this redshift dependence in our simulation. The masses of them, size-wise, well, they're pretty compact. I mean, so they're much compacter than local galaxies. So these are the dark matter profiles I was mentioning earlier. So the second thing we wanted to look at is actually what's the effect on the hosting dark matter halo in our simulation. And what we did is, for that, we ran actually two simulations, one with including baryons and all the physics, and one dark matter only simulation based on the same initial conditions. Okay? And so the black dots here show the dark matter only runs, and the blue show the profiles for the same identified halos in the runs, including the baryons. So what you see here is, I mean, one thing was we needed to make sure that we, of course, identified the same halos, and we took much care in trying to do that. So what you see is we find halos in which, of course, the dark matter profile seems to be increased with respect to the non-baryonic simulation, which is here shown. The baryon simulation have more dark matter mass inside a certain radius than the dark matter only run, which you see here 3 examples for. But we found also the opposite. We found halos in which actually, when you have baryons, the dark matter profile is less enhanced inside. So basically the opposite of some kind of adiabatic contraction. Now, we were quite puzzled by that, and we tried to understand it in more detail. So first of all, we looked into the distribution of that in our simulation, and we found that actually roughly 50% show an enhancement and 50% show actually a decrement. So, and for the remainder of my talk, I mean, we define enhancement as something which is more dark matter mass within 0.1 RVR in the simulation with baryons than in the simulation without baryons. Okay, so that's our definition of enhancement. So everything to this side is enhanced because there's more mass within 0.1 RVR. Now, if you plot the enhancement versus the amount of baryons that you find within 0.1 RVR in a given dark matter halo, then you find actually this nice kind of strange figure with all those relations, if you like, you see. So what you would naturally expect is that if you have lots of baryons within the core of a dark matter halo, that the dark matter halo reacts, adiabatically contracts, and you get an enhancement, okay, going in that direction. And this is in fact what you find, and the results are in very astonishing good agreement with the modified adiabatic contraction model by Nick Nedin. So what we then did was to say, okay, well, what is the reason then for these guys? These kind of like confused us, and this is work in progress. We're trying to understand what's going on there. So how can you have lots of baryons, but the dark matter halo profile is actually expanded? You have a core, you don't have an enhanced amount of dark matter in the center. And then there's the whole bunch of galaxies with decrements where you have a range of baryonic fractions in the center. Now, we looked, first of all, into the evolution of the enhancement with respect to the star formation, the underlying star formation, the host galaxy going on. So what you see here as black is the enhancement. So above the red line, the dark matter is enhanced in the center. And what I show you here as blue is the star formation rate in that galaxy as it's going on. So we shifted the star formation rate just to overlay it with the enhancement. So there's no units for it yet here on the plot. But what you see is very interesting. So if you have a burst in star formation, so if star formation is going through a burst due to inflowing material, you have also an enhancement of the dark matter. So the dark matter responds to the inflowing gas in terms of adiabatic contraction. Now, as the star formation ceases due to feedback effects, the dark matter responds as well because you blow out material and it goes down again in the same vein as the star formation that goes down. And you see that happening in many cases. Now, something that's interesting is here, for example, look at this little burst of star formation. So you have an inflow, you have an enhancement, and then the star formation shuts down because of the blowouts, but the dark matter profile doesn't go back initially to the same state as it was. It seemed that you managed to actually put some energy into it, into the dark matter. And people have been looking into that and finding actually that if you change the potential on such a fast timescale, and it's worked by Ponson and Governato, you can actually inject energy into the dark matter halo and generate a core. Now, what we found, and that was very surprising to us, as a cause of basically a possible cause for that decrement of dark matter in the center, was that when we looked at the baryons, the galaxies, and tried to see where they are with respect to the potential minimum of the hosting dark matter halo, there was an offset. And there was a nice tight relation between the offset of those galaxies with the enhancement. So if you have an enhanced galaxy, there's usually a dark matter halo, there's usually not much offset between the galaxy and the potential minimum of the dark matter halo. If you have, however, a decrement, there seems to be a larger enhancement. Now, we interpreted that as the galaxy actually being able to convert its orbital angular momentum while it's orbiting around this potential minimum into angular momentum for the dark matter halos and heating the dark matter in the inside and pushing out dark matter from there and generating the decrement. So this is something we, of course, now need to understand a bit more in detail and looking into it right now as we speak. Now, since my time's up, let me just bring up the conclusions. So within our simulation, and I must say, of course, there's a caveat that our box is not so large that we have high sigma fluctuations. However, within our simulation, we find that the universe can be ionized by baby galaxies, these really efficiently star-forming galaxies, galaxies with masses below 10 to the 6 solar masses. The reason for that is that they have high escape fractions due to supernova feedback being so efficiently in blowing channels and letting the photons escape into the IGM. We find that the escape fraction is has a large dependence on mass. So massive galaxies are have not that high escape fractions as low mass galaxies, just because the feedback was not yet so efficient in driving channels through the ISM. We find that dark matter halos, actually they can contract and also expand. You can make a core in them. And that actually, within our simulation at least, that the features of a dark matter halo profile, the inner features of dark matter profile, are actually transient features. So if you find a halo that is contracted and you find one that's not contracted, it's actually a natural outcome of feedback, of the movement, in our case, of the orbital angular momentum transfer of the satellite into the dark matter halo. So the very surprising thing, and that's the last thing I'm going to say, that we found was really that all these galaxies are offset from the potential minimum, and we're now trying to understand why is that the case. Is that because there's a merger going on? Why is it that the galaxy doesn't live in the potential minimum of the dark matter halo in so many cases? Okay, I will stop here. Thank you.
Right, we have time for some questions.
So you find that universe is at redshift of 10.5. Have you made predictions? I mean, you showed the comparison with redshift 6 observations of, say, the stellar mass, star formation rates. Have you made predictions for what people should see at redshift 10 for the star formation rates?
For the star formation rates?
Right.
Yeah, we can do that. I haven't shown the plot.
Do you predict many more galaxies than what people saw? Or should have seen?
At a higher redshift, higher than 6.
Exactly.
Well, I mean, the thing is, we are actually probing mostly fainter galaxies than you see at this point. So that's the problem. So we cannot see it. It's more than you see because you don't see any, right? So that's the problem. But since our box is not so large that we have even more massive galaxies that come into the observational range. So that's my answer for that. I should, maybe, since it fits actually what you were asking. So we actually tried to make predictions for JWST. Would you see those small baby galaxy reionizers? And in UV continuum, it will be very difficult. So we took one of the deep surveys that you would see with JWST, with NIRCam, and you would only really see these galaxies, 10 to the 8 solar masses and more massive at lower redshift. These you wouldn't see, which really cause reionization. However, in H alpha you would see them, and that's the good news. So in H alpha we would still see them even up to redshift 10, right? So we don't see them yet, but in future, hopefully.
Left.
I missed how you want the star formation.
So what we do is basically we resolve the collapse of the gas till we reach 10 particles per cubic centimeter densities. And then we assume the Shire and Dalla Vecchia pressurized star formation law. So we didn't base it on H2.
No objections to the escape fraction.
Oh, yeah.
If you take a single H stellar population, like a cluster, then most of stars, most stars they produce most of ionizing photons never really blow up as supernovas. They go into black holes directly. So for normal stellar populations, almost independent of metallicity, 90% of ionizing photons are emitted before the first supernova explodes. So I challenge you to explain how you can use supernovae to get more than 10% escape fraction.
Well, I mean, here's the answer, I think.
Because that cannot be physical, right? 90% of ionizing photons actually emitted before the first supernova explodes.
But look at this. So this is the point where spiky star formation rate actually comes quite in handy, right? So you have the star formation burst, and as you said, you produce those ionizing photons. Then, basically, everything first shuts down, okay? You have the first supernova then going off here, starting to make the channel. Then you have the next episode of star formation that again produces photons, which actually go off in a region that was already affected by supernova feedback. No, sure, certainly. Well, I mean, to be honest, yeah, of course you're right. We don't resolve that high densities that we can really say what is happening in gas of densities above, 1,000 particles per cubic centimeter, right? But nevertheless, sorry?
He's saying that a large fraction of ionized photons will be absorbed before you supernova.
Yeah, that's what I'm trying to say. I mean, we don't have those high densities.
Reionization time scale is more because you reduce the ionization fraction by factor of 10, but then you have universe with small galaxies.
But then, I mean,
Since we're having this discussion, let me just add something that I was hoping Charlie Conroy would mention, because he's got a paper on this. And that is that something like a third of these massive stars actually escape the high-density gas region in which they form, typically due to three-body effects, sometimes due to unbinding because one of the stars supernovas, but it's more commonly three-body effects. That means that those stars actually can radiate outside of the dense regions that are going to typically absorb their radiation. As far as I know, that's not taken into account in NICS simulations nor in Sadegh simulations, but at least according to Charlie, it could have a significant effect on reionization. Any comments?